Hi, everyone. So my name is Han, and I'm a second-year PhD student from Quantitative Life Science at McGill. So thanks for joining this 2 days workshop, and I will be leading this data visualization session. So here's our learning objectives. So this workshop is to provide some basic and advanced techniques for data visualization in R. And by the end of the session, you should be able to apply data transformations and faceting to improve interpretability and comparisons across data sets. And also you will learn to customize plots for clarity and impact, and also create interactive visualizations using the Plotly package, and understand how to select the right type of the plots for your data storytelling needs. So by the end, you should feel more confident in designing visualizations that are informative, aesthetic, and interactive. So today's workshop is structured into three main modules. So the first module will be a brief view of basic visualization in R, covering the structure of our ggplot2 command and its components. And the second module will focus on advancing customization and data transformation, where we will explore data transformations, faceting, aesthetic customizations, and legend modifications. So the third and final module will introduce more advanced visualization techniques. We will learn some specialized plots and interactive visualizations. If time permits, we will have a chance to create an R-Shiny dashboard. So let's jump to the first module. So when we talk about data visualization in R, the most famous package we use is ggplot2. So this package is very useful for data visualization. So most of you may know this package. However, many people don't know why it is so powerful. So here is a table that illustrates the differences between ggplot2 and base R in data visualization. So compared to base R graphics, ggplot2 package provides better aesthetics, higher efficiency. Base R often requires writing additional lines of code and manual adjustments, so making it less intuitive and harder to maintain when creating complex visualizations. So that's the reason why we prefer ggplot2. So the reason behind ggplot2's effectiveness lies in its underlying concept, the grammar of graphics. So the first two GG character means grammar of graphics. So it uses layers to describe and build graphics. So this process is similar to how we draw a watercolor painting. So imagine first we put the data set into the device, and second, we create a new layer to specify the type of the graph and the variables to use. And then we create new layers to add labels and the titles to the plot. And last, add a new layer to customize the look of the plot with themes. So there are several different components and parameters in ggplot2. So the first three, the data and the aesthetic attribute and the geometric object, these three are the required ones in a plot. So the right side shows the structure of a plot using ggplot2. So you can see like here we indicate the data we will use for the plot. And the second, we add the geom function to indicate what type of plot we will use. And here shows the aesthetic part. It shows like what's your x-axis and what's your y-axis. Okay, so the rest are the other parameters we will use in a plot. So the basic structure of a ggplot2 command begins with defining the dataset and statics. So followed by adding geometric objects to represent the data visually. So the aesthetic attribute can be defined either inside the ggplot part to be a global aesthetics, or in the geometric object function to be a local aesthetics. So when the aesthetics are defined inside the ggplot, they are globally to all layers in the plot. And this means that every geom function added to the plot will inherit these mappings unless overridden. So we can see this is a very simple example. So if we want to know the relationship between the biolength and biodepth of the penguin, like here, shows here. So we want to draw a scatter plot to show the relationship between these two variables. So here, very simple, we have our data set, we have our type of layers, type of plot we want to draw, and also we have the aesthetics part for the plot. So in this session, we will use a built-in data set in R named GapMander, so which contains concept of the GapMander data on life expectancy, GDP per capita, and population in 142 countries from 5 continents, from 1952 to 2007 in increment of 5 years. So here are the first 5 observations from this data set. So we can see the first column is country, the second column is the continent that this country from, and the third column is the year, and fourth is the life expectancy. The fifth is the population, and the last one is the GDP per capita. So next we will go over some basic plots using this data set. So the first plot is a bar plot. So you may see the bar plot from many papers. So the bar plot is used to describe the frequency of the discrete variable. So here is a bar plot to describe the number of recorded observations distributed across different continents. So the x-axis is different continent, and the y-axis, you can see here, is a count, like the number of observations in the data set in each continent. So you can simply use the geom bar function in the ggplot to draw a bar plot. Okay. So next one, I will introduce the histogram frequency and density plot in one slide because they are very similar to each other. So these 3 plots are all used to describe the distribution of a continuous variable. So for example, the following 3 plots describe the distribution of life expectancy among different continents. However, these plots differ in how they display information and in their best use cases. So first one is the histogram. So the histogram uses bars to represent data distribution, and the beam width wise, you can see here, we set is equals to 1. So it affects how detailed the distribution appears. So in this case, it visualizes the overall trends in life expectancy, the x-axis, while stacking data from different continents. So from a broad perspective, we can see that the highest concentration of life expectancy falls around 70 years old. And looking at individual continents, the Africa, the red one, you can see here, it dominates the lower life expectancy range of 30 to 50 years old. And while the Europe one, the blue one, and the Africa, the green one, these two shows peak at higher life expectancies. So a histogram is used to gain a quick overview of a data set's overall distribution and how different categories stack within it. Okay, so the second one is the frequency plot. So we use the frequency plot, like it uses the lines instead of bars while maintaining count information. So this method allows us to visualize the trends more clearly than a stacked histogram, especially when comparing like multiple groups. So here we can see it compares like 5 different continents, 5 different groups. But however, we cannot get information for the overall distribution of the life expectancy through the frequency plot. The separation of lines make it easier to identify the patterns in different categories. So for example, in this data set, we can see that the Europe, the blue line, peaks around 75 years old, and the red line, the Africa, has a broader distribution below 50 years old. So the America, the green one, and the Asia, the crayon one, have wider distribution between 50 to 70 years. Okay, so the last one is density plot. So the density plot further refines the visualization by smoothing the distribution into continuous curves. So instead of count, the y-axis represents the probability density, meaning the area under each curve sums to 1. So regardless the size of the data, we can directly compare the shapes of the distribution without being misled by the absolute count. You can see here for the frequency plot, the y-axis is the absolute count, and for the density plot, the y-axis is the density, the probability. So thus, the density plot is very useful for peak identification. So for example, in our data set, we can have a clear observation of the distribution of life expectancy in Oceania, like the pink one. Here, we can directly see the distribution of the data set, but we cannot observe it very clear in our second plot. So because the size of the data set, the subset is too small compared to Europe or Africa, so we cannot observe the distribution of it in the frequency plot. So we could use density plots to focus on the shape of the distribution within each group rather than comparing the absolute values. So here are some tips for choosing the right plot. And here's 3 research questions. Try to match them with these 3 plots. So we can go over it one by one. So the first research question is trying to identify the peaks of the distribution. So we can match it with the density plot because it asks, does the distribution of life expectancy in a continent suggest the presence of the distinct group? Everyone get it? So the second one, second research question asks, what is the overall distribution of the life expectancy? So this one, we investigate the overall distribution. So we should use the histogram because the histogram is used to show the overall distribution of the whole data set. So we can match this research question to the histogram plot. Okay, the last one compares the life expectancy across different continents. So this one is trying to compare the distribution across different continents. So we can use the frequency plot. So this is differences between these 3 plots. Okay. So the next plot I will introduce is a box plot. So here is a box plot to describe how life expectancy change over time. So you can see the x-axis is the year, the time, and y-axis is the life expectancy. So the box plot is used for 1 discrete variable and 1 continuous variable. So you can simply use the geom box plot function to draw the box plot in the ggplot2. Okay.
I had a question about the previous one. So before when we showed the structure of the ggplot command, we showed that, say, the aesthetics argument was always with the geom function. Say, for example, here it seems you can also provide it to both. So usual is the practice always to, in this case, is it required to separate the aesthetics function, or it could have all been the same part of the ggplot?
You mean the aesthetic part? Yeah, for this example, you can see that the aesthetic part is in the geom function. So this is, it will only affect this this function, this layer. But if you put the aesthetic, like for here, like the in the ggplot function, it will affect all the layers in the plot. Yeah, for the bar plot, this line shows the mean, and the two lines on the each side shows the error bar. Like, I believe it's 25% and quantile information. I think, yeah. So the violin plot. So the violin plot is a combination of a box plot and a density plot. So it can both show the information from these two plots and combine them. So if your goal is to visualize the shape of a single distribution, use a density plot. But if your goal is to compare the distributions across multiple categories, you can use the violin plot. So if you want to explore whether a continent has two distinct life expectancy groups, the violin plot is better than the density plot because it allows easy comparison between continents and shows multimodal distributions more clearly. However, be careful when the size of the data set is small. The violin plot is not a good choice because this plot will it's because the density plot is a smooth one. So like even though there are the lines, but maybe there is no data at that point. So be careful when your data size is very small. So let's see an example of how to improve a data visualization plot step by step. So in this exercise or in this example, we use the built-in Lincoln weather dataset to investigate the weather distribution of Lincoln in the USA. So the Lincoln weather dataset containing weather information from Lincoln City in the United States from 2006. So what question do you have about this plot? Sorry? Gaussian curve? You mean like here? I don't think this is Gaussian curve. Yeah, but you can see like this plot is it shows the information more like a box plot. Like maybe here the point is a mean or median, we don't know, right? And here is a bar plot, but we don't know like this bar, the meaning of the bar plot, this bar, like the error bar. Is it mean the standard deviation or standard error or something else? We don't know, right? And also like we know that real data is often skewed. Yeah, but the error bars in this graph, in this plot, are almost symmetrical. So can this represent the distribution of real data? So we don't know these questions, like, right? So to enhance the visualization, we use the box plot or violin plot to show the distribution of the real data, the temperature. So you can see this is the box plot and this is a violin plot. It's much better, right? It can show the distribution of the real data. So comparing these two plots, we can see that the violin plot, this one offers additional insights because in November, you can see here, the violin plot reveals two distinct temperature peaks. So here and here, but we cannot see this information in the box plot. But the violin plot is also not that perfect because it relies on the density estimation. So it can create the illusion of data in areas where no actual points exist. So how can we address this issue? So we can display the original data set, the original data points. So, but however, there are a lot of overlaps in the left plot. So how should we do? We can use the jitter plot to help mitigate the problem of overlapping points by adding a small random offset to each data point. So here is a data plot. It can show all the data set, real data. So finally, we got the Sina plot, which combines the advantage of both the Welling plot and the Jita plot. So here. So it shows the overall distribution. We are also displaying the raw data set, providing a more comprehensive view of the data. So here. So do you have any questions for the first part? Okay, cool. So we can go to our second part. So this module will talk about data transformation and advanced customization in data visualization. And I noticed that in yesterday's workshop, you have already learned the dplyr package, like this one. Do you remember? Okay, so for the data transformation, we will also use the dplyr package. It's a very useful package in R. So before creating meaningful visualizations, it's often necessary to transform data to ensure the clarity, accuracy, and interpretability of the data. So this slide outlines several key data transformations, techniques, and the corresponding functions used to achieve them. So the first transformation technique is data reshaping, and this one is particularly useful when working with faceted plots or grouped variables. So the function pivot longer and pivot wider function from the tidyr package help reshape the dataset between the long and wide format, making them more suitable for different types of visualizations. And the next one is filtering rows and selecting columns. So these two ways allow us to focus on relevant data while removing noise and unnecessary variables. So the filter function helps subset rows based on conditions. And the select function is used to keep only the necessary columns we used to draw the plot. And this step ensures that the visualizations highlight the most important aspects of the data. So the next one is aggregation and summarization. So these two are essential for transforming raw data into summarized statistics that are easier to visualize. So the function group by and the summarize, these two functions in the dplyr package allows us to compute some key metrics such as the means, counts, and sum. So these functions are very useful for the bar charts, the summary table, and trend analysis. So the next one is normalization and scaling. So the normalization and scaling ensures fair comparisons across different numerical ranges. So this includes log transformation, minimal, min-max scaling, and z-score standardization. So the mutate function, this one is also in the dplyr package, is commonly used for these transformations. So you can also use the scale x log 10 function for a log transformation in ggplot2. So we will look a log transformation later. So the last one is binning or discretization. Okay. So it involves converting the continuous variable into discrete categories, making it easier to visualize distributions. So this is also done use the mutate function, and where the values can be categorized into groups based on the predefined ranges. So by applying these transformations, we can enhance the clarity and interpretability of our visualizations, ensuring that the data is presented in the most effective way. So next, we will use the log transformation as an example to show the necessity of data transformation. So here is a simple example of log transformation. So for example, we would like to investigate what is the relationship among the GDP per capita, life expectancy, and population across different countries in each continent. So here we can see we use the GDP per capita in the x-axis and the life expectancy on the y-axis, and demonstrate the population through the size of the points. Like you can see here, the different size of the point shows the population level. So from the left plot, we observe that the GDP per capita is highly skewed, especially with a few countries having very high GDP. You can see here, this point. So this can make the plot hard to interpret. So the point of the high GDP value might dominate the visual representation. So thus we perform the log transformation on the x-axis. So from the right side plot, after performing the log transformation, we can see that the relationship appears more linear with the log transformation. So meaning that each incremental increase in GDP per capita has a more proportional effect on the life expectancy. So it makes it easier to observe the relationship between the economic growth and life expectancy, particularly in low and middle income countries. So here the data are more visible to us. Okay. So next, I want to talk about data visiting. So this is a very useful techniques or tips for like data visualization. So data visiting is used in data visualization to break down the data into subsets and display them across multiple smaller points, smaller plots. So there are two ways to apply the visiting in ggplot2. The first method is to create a structured grid of graphs arranged by rows, like here, or columns. Like this is row and this is by column using the visit grid function, this function. So the other one is to generate the small multiple by wrapping a series of plots into a flexible layout using the visit wrap function. You can see here. So you can choose the one based on the structure of your data and how you want to show the comparisons. So here are some tips to help you decide between using a grid or a wrap. So use the visit grid function when you need a systematic comparison between different subsets. And it works best when the number of visit levels is not too large, as too many rows or columns can make the plot difficult to read. And on the other hand, the visit wrap is more flexible and space efficient. So especially when dealing with a single categorical variable. So instead of enforcing a straight and grid layout, it automatically wraps visit across multiple rows and columns to make better use of available space. So the next one, I would like to introduce the color palettes. So choosing the right color is essential for effective and interpretable visualizations. So different types of data requires different color mappings to highlight the patterns, relationships, and variations. So here I introduce a very useful package named Color Space. So it provides great color palette to create plots based on different data types. So there are mainly three color scales: the qualitative one, the sequential one, and the divergent one. So the qualitative one is used for the categorical variable. The sequential and divergent one is used for the ordered or continuous numerical variables. But please remember, don't use the bidirection or diverging color scales for unidirectional data. It may cause some confusion. Okay.
What would you describe as unidirectional data in this case? What example of a range of values you see as unidirectional, bidirectional?
You can see here, like, this is a bidirectional data scale because it has a middle color. It's with a lighter color here, shows here. And for each side, it shows the color will go deeper. So this is a bidirectional. And the sequential one is shows here. So the color will go lighter to dark, like for the sequential one. So here is how to use the color space in ggplot2. It's very simple. Like you can just simply add a layer to the plot with the following code to adjust the color. Like you can use the scale color discrete qualitative one to apply the qualitative color palette to your plot. And also like same for the sequential and divergent. So here are some examples. So these examples of color space is to give you a sense of what color scale you should use based on your data and your research questions. So we can see the first plot. So the first example uses a qualitative color scale to distinguish categorical variables. So here we visualize the built-in ERAS dataset by creating a scatter plot of sample lengths versus sample width, like you can see here. So with points colored by species. So here are 3 different species of the flower. Iris is a flower. So since the species is a categorical variable and it's a distinct color, so we can use the distinct color to assign to each category without implying any numerical relationships between them. So like these 3 colors, they are like at the same level, so they don't have any numerical relationships. So the second plot, the top right one, applies sequential single hue color scale using the built-in empty cars data set in R. So this bar plot ranks the car module based on miles per gallon on the y-axis. So with a single hue gradient from light to dark. You can see here, this is the light part and this is the dark part. So this plot indicates increasing miles per gallon values. And the sequential color scales are useful when mapping numerical variables, where higher values are more intense than lower ones, so making them ideal for ranking or progression-based data. So the third one, the bottom left example, we use a sequential or multi-hue color scale to visualize the built-in volcano data set as a heat map. So this provides a 2D topographic view of elevation data. So where the changes in color intensity represent the variations in terrain height. So multi-hue sequential scales are particularly useful in heat maps when we need to show smooth transitions across a continuous range, and such as elevation, temperature, or density. So the last example, the last one, demonstrates a diverging color scale using a built-in United States RAST data set. So the goal is to understand how urban population percentage of each state in the United States compared to the median urban population percentage. So the divergent scale helps differentiate the states above and below the median urban population percentage, using 2 contrasting colors to show the positive and negative deviation. So here is a positive part and here is a negative part, and between them there is like a middle middle color shows the median urban population. So by choosing the appropriate color scale, we can improve the clarity and interpretability in our visualizations. And the codes of this example plots are all provided in the RMD file from the materials we provided. And you can check this the code for more details for this plot. So sometimes it's hard to choose the diverging or sequential color scale because both of them fit ordered and continuous data. So diverging color scale and sequential color scale tell totally different stories. So here are some useful tips. So you can use the diverging shades if there is a meaningful middle point, and if you want to emphasize the extremes or the outliers, or you want let the readers see more differences in the data. So this is an example from the attached blog to illustrate how to differentiate the diverging and sequential color. So imagine you write a story about how the internet is mainly populated by or benefiting Europe, United States, Japan, Australia, or some other countries. So you might choose to use the sequential color scale to emphasize the countries with the highest value, like here. If, however, your story also want to show how few people use the internet in Africa and Asia, so then you might choose to use the diverging color scale to show the contrast and differences. So the following two circles represent Russia and Turkey. So you can see this one is Russia and this one is Turkey. So the Turkey looks only slightly lighter than Russia on the map with a sequential color scale, although they are like 60% points apart. So in the diverging scale, the differences is bigger. You can see here, like the Russia still has a similar blue, but the Turkey looks far lighter and more beige. So indicating it's closer to a middle point. So you can see more differences with the diverging color scale. Yeah. So you can choose to use the diverging or sequential color scale based on the story you want to tell. So choosing the right color palette is also important for interpreting heat maps effectively. So since the heat map use color intensity to represent the numerical values, so selecting an appropriate color scale ensures that the patterns and trends are easily distinguishable. So the left side plot shows the default color scale of the heat map. So it may not be the best choice for distinguishing the differences in values, as darker shades can sometimes blend together. So by using well-designed sequential palettes like the Veritas and Inferno, like we can improve the clarity and effectiveness of heat maps, ensuring that the key patterns in the data are clearly visible. So these two, we use the defined Veritas and the Inferno color palettes to better show the pattern of the heat map. Okay, so the next part is about the size of the points and the transparency. So we can simply add the parameters size and alpha in the geom function to change the size and transparency of the points in the plot. So the alpha is between 0 and 1. So 0 means completely transparent and 1 means completely opaque. So it's very easy, just add the size and alpha parameters. Okay. So then we come to the legend part. So I met with a lot of problems with the legend in my previous experience when I tried to create some complex plot. So the legend play an important role in interpreting the plot. So below, we will explore how to adjust its appearance, create different legends for different layers, and learn how to delete or merge the legends. So the guide function in the ggplot2, like here, is a high-level way to control the appearance of guides of the legends. So which includes the legend and access guides. So it specifies how to handle the mapped aesthetics in the legend. So when we draw a scatter plot like here, we may set the transparency and size of the points. And this method is more useful when there are a lot of points, but it will also lead to the legends. So like here, you can see that the legend, it has the same size and transparency of the points in this plot. So we want to change it to like more visible. So so here, so we can use the override aesthetic in the guide legend function, like here, to override the default legend. So for example, here we would like to modify the legend corresponding to the size and transparency. So we can simply use the code here, like the size equals to 3 and alpha equals to 1 to override the legend on the in the left plot. So here we have the new legend. It's more visible for the readers. Okay. So here we added a fitted line to the scatter plot. So how to add a legend to illustrate the original observations and the fitted line. So here we only have the observations, but we don't have the legend for the fitted line. So since ggplot2 assigns the legend based on mapped aesthetics, so we can use an unused aesthetics like alpha to differentiate the point layer and the fitted line layer. So what does that mean? So our intention is not to modify the actual transparency appearance of the plot using alpha. So we define alpha as equal to observed in the point layer and alpha equal to fitted in the fitted line layer. So instead, we later override the alpha with the scale alpha menu function, like here, setting the real values of alpha into in two layers to 1, and ensuring both layers remain fully opaque. So after defining the menu scale, we remove the legend title by setting the name to none. So we also control the legend order using the break, making the observed appears first, like shows here. So finally, we customize the legend appearance using the override aesthetic function. So you can see after this modification, we have the legend shows here, like it also shows the observed data point and also the fitted line in the legend. So next one is how to delete the legend. Yeah, it's very simple. You just let the legend you would like to delete equal to none. Yeah, like here. So the legend you don't want will be deleted. So the next part is how to merge the legend. So we can see here, like both the color and size use the body mass G mapping. So it's we use the same variable for the color and size. So we will have two different legend, but shows same information. So here we want to like merge these two legend. So one way to merge the legend is by defining the guides for both aesthetics and assigning them to the same guide legend function, like here. So this tells the ggplot2 to treat both the color and size as part of the same legend. And another way to merge the legend is by specifying guide to legend here. directly in the color scale function. So we are telling ggplot2 to treat the color scale as part of the shared legend, which allows it to merge with the size scale, since both color and size are mapped to the same variable. So these two ways can merge the legends, and finally the plot will only have one legend, shows both the size, both the color and size, shows all the information we want.
Add something. So remember this, so you worked with the pipe operator fire. So there is focusing on doing itself. But you'll notice if you look at the top, just under method 1, you'll see that the actual data frame that we're using to generate the plot is being put pipe into the plot. So the dpipe package isn't just limited to modifying the data set, it actually combining modifications with piping directly to your visualization. So let's say you don't want to modify the plot data frame you're working with, you can use the pipes to do modifications you looked at yesterday, and then also send the pipe directly to the visualization. So all of that's combined essentially. There's not even separate stuff. Really good advantage of pipe splitting, combining everything from the raw data all the way to the visualization.
So here, the ggplot2 also provides several built-in themes that you can apply directly to your plots. So such as theme minimal, theme classic, and all these functions you can use to adjust the theme. So each function will offer different styles and levels of details. However, if these default themes don't fully meet your needs, you can also like customize your own theme using the theme function. Like which one? Yeah, only this one. The theme. You can only write theme theme. And this function you can like customize your own theme. And you can modify various panel elements like the background color, grid lines, and legend placements to best suit your visualization. So, okay, here comes to our first exercise. So for this exercise, you will refine the given plot to enhance its clarity and aesthetics based on the following requirements shows here. So you will have 10 minutes to complete this task, and feel free to use Google to use ggplot2 cheat sheet as needed. So the next part I'd like to introduce to you is the specialized plot. So in this session, we will explore some specialized plots that are designed for some specific types of data and analytical needs. So the first one is heat map. So you may see the heat map in many papers. So here is how to how to make the heat map. You can simply use the heat map function in base R, or you can use ggplot2 to draw the heat map with the geom tile function. And also you can use the p heat map for annotated heat maps. For example, this one is annotated heat maps. So you will have some annotations like the y-axis or x-axis to show the exact meaning of the heat map for each row or columns. So the heat map is a powerful visualization tool that represents data values using the color gradients, much like a thermal camera image, where different temperatures appear in distinct colors. So instead of showing temperature, a heat map shows the intensity correlation or the frequency of the value. So making the patterns and clusters easy to identify. So you can use heat map in the following situations, like you want to do a correlation analysis or some feature, you want to show the feature importance in machine learning and something like that. So it's very useful. Okay, so the next plot I would like to introduce is KM curve. So the KM curve is very useful in survival analysis. It is used to estimate the survival probability over time. So it's like a long distance race. So the runners drop out over time due to death, quit, or failure to follow up. So the curve steps down each time someone drops out. So showing the survival probability at different time points. So the KM curve is ideal for clearly visualizing survival differences over time between groups. Like here, we have two groups, the male one and female one. And it is very useful in the randomized control trials, the RCT. And the shape of the curve reveals trends in survival probability and event rates. So you can use the GG survive plot, this function, to generate the KM curves. So the next plot I want to introduce is the Manhattan plot. So the Manhattan plot is used primarily in genome-wide association study, GWAS, to visualize the p-value across genomic positions. So this plot looks like a city skyline, like where each building represents a genetic variant. So the tallest skyscrapers indicate the strong associations, like here. And his horizontal axis represents the genomic position. So here we have 22 chromosomes. So the x-axis represents that. And the y-axis shows the strength of the association. So the Manhattan plot is can easily highlight the significant genetic variants that stand out from the background noise. And also it helps quickly identify the genes or regions in the genome that are related to the disease. The last specific plot I would like to introduce is the 2D density plot. So this plot works like a weather radar. So where more intense areas shows more storms or more data points are concentrated. So like here, you can see in this plot, you can see maybe here are more data sets, they are overlapping with each other, but we cannot figure it out. But with the 2D density plot, you can see here. So the color indicates the density of the data point. So here, like here have more data overlap here. So instead of plotting every data point, it visualizes where the highest densities occurs and helping review clustering and patterns. So the 2D density plot is great for handling large data sets with overlapping issues in scatter plots. And it can clearly highlight the regions with high concentrations of data points, making the trends easier to interpret. Okay. So here are the two for specialized plots I share with you. So the next session is about the interactive plot. So this is more advanced visualization techniques. So so we will learn how to draw the interactive plot. So let's first see this plot. So we have been very familiar with this plot, like the relationship between the BioLearns and BioDepths for the penguin. So but right now this plot it means clear labels and ways to tell different groups apart. So think about how we can improve this. Like what extra information could make this plot more useful and easier to understand. Like some observations or some data or some information we like to add to the plot. But before that, we can first check the data, like the data we use to draw this plot. So looking at the data set, we can see that the variables like species and island may add more context. So instead of treating all data points as one group, we could color them by species to see if different species show different characteristics. So like here, we color the data points with the 3 different species, but this brings us another question. So what if we are still interested in the individual data points? Like right now, the static plot doesn't give us any extra details about the points. So we can try ggplot to provide more details. So one way to make our plot more insightful is to make it interactive with ggplotly. So this allows user to hover over points to see more details. So it's very simple to use. Just call this function, the ggplotly function, after you create a plot, and then you are done. So now we can see the exact biolearns and biodepths for each data points when we hover over the data points. And this simple function called turns your ggplot into an interactive plot. But here it's a static, but we will have a chance to try it later. So this interactive plot makes it much easier to explore the data dynamically. Yeah, but right now we can only see which species each penguin belongs to. So what if we are interested in which island it's from? So let's take this one step further. So by default, ggplotly gives us some basic hover functionality, but we can customize the tooltips to show more useful details. So to do this, we first create a custom test column that includes all the information we want to display, like like here. So besides the island and species, biolearns, biodepths, we can also show other information of the data point, like the flipper length and body mass. So so finally, in ggplotly, we set the tooltip equal to test, like what we defined here, to make sure that our customized tooltip appears. So now when we hover over a data point, we can see not just the species, but also the island, the biolearns, the depths, flipper length, and the body mass of each penguin. So this makes it much easier to explore the data set in detail. So to make the tooltips even more readable and visually appealing, we can customize their appearance using the HTML formatting and adjust the hover label styling in the layout function. So for example, we want to change our the information or the style of the tooltips shows like this way. So we can simply apply the HTML tags. We can format the text, making key details stand out, like here in a HTML format. And then with the layout function, we can modify the tooltips background color, here. So here we change the background color to white, and we change the font size to 12 and the color of the text to be black. So with ggplotly, we have moved our plot from a basic scatter plot to a fully interactive, customized visualization, so allowing users to explore and extract the insights interactively. So the static plots are great for visualizing relationships at a single point in time. But what if we want to see how these relationships change over time? So this is where ggAnimate comes in. So the animations are produced by transitioning between different layers of a GG objective over time. So which can be especially useful when you want to visualize changes in data or trends. So we have already seen this figure before. So it describes the relationship between GDP per capita and life expectancy across different continents. So each point representing a country. So, but instead of just showing a single snapshot, GG Animate allows us to animate the data over time, so making it much easier to see trends and dynamic changes in the data. So you can use this GG Animate function to control how data points move, how positional scales change across an animation, and how your new data appears over time. So there are some parameters in the GG Animate. So you can adjust the parameters to create your own type of your own type of plot. Yeah. So this resource offers great tutorials on GG Element. So you can, if you are interested, feel free to explore and try this out. And the code for this plot is provided in our Markdown file. So you can try it if you are interested. So this part will be the our Shiny dashboard. So Shiny is an R package that lets you build interactive web application directly within R. So this makes it a powerful tool for data visualization and interactive reporting. So unlike static plots or dashboards, Shiny allows users to interact with data in real time, like modify the inputs, the parameters, and instantly see how output changes. So it's very user-friendly. People without any coding experience can use it very simply. So the Shiny app consists of two main parts, the user interface and also the server. So the UI part controls the layout and appearance of the app, and the server handles the computations, data processing, and rendering outputs based on the user inputs. So to design the UI, Shiny provides different layout functions, and we will explore them shortly. But before that, let's first see an example. So this example, this dashboard provides 15 different popular visualization analysis methods, like the heat map, cluster analysis, KM curve, PCA, ROC analysis, and some others. So like, for example, so this is, I think this is a heat map one. So here you can run the example they provided. So here it shows the heat map it created, and you can also upload your own data set. So this dashboard enables the experimental biologist without programming skills to easily perform popular visualization analysis and get publication-ready charts. So let's dive into the R Shiny, like how to create a website like this, but not this that fancy. We will like learn some basic functions or some basic techniques to like build our own R Shiny app. Okay, so first, let's see the skeleton of R Shiny. So we have already know that the R Shiny is designed by two different parts. So the first part is the user interface, and the second part is the server. So like, so the user interface defines the visual layout, and the server handles the reactive behavior and interactions. So for example, the UI, like the user interface, will define what the user sees, like including the input controls, the plots, the tables, while the server processes the inputs and updates the outputs dynamically. So the code to generate a simple RShiny app consists of 3 components: the UI object and a server function, and lastly, a call to Shiny app function to connect these 2 parts. So, okay. So this is the structure of a Shiny. So you can see the first layer layout is page. So a page defines the top level UI structure of a Shiny app. So it determines how content is organized across one or multiple pages. And the function fluid page is a layout function used to create a responsive web interface that automatically adjusts to different screen sizes. So it ensures that the UI elements, such as the plots, tables, or input controls, resize dynamically, making the application adaptive and user-friendly. And the fluid page is a great starting point for building adaptive, user-friendly Shiny applications. So the next layer is the layout. So the layout defines how elements, such as the inputs, outputs, and tests, are arranged within a page. So it structures the user interface to make it clear and user-friendly. So we will see the commonly used layout shortly. And then the next layer is a panel. So a panel is a smaller section within a layout that hosts the UI components like test, plots, tables, and inputs. So here shows the layout and the panel. So when building our Shiny app, we need a clear and structured layout to make sure everything is easy to use and visually organized. So here are 2 commonly used layout and panel. So the first one is set bar layout, and the second one is table set panel. So the set bar layout is the most popular layout. It splits the page into 2 sections, a narrow set bar, like here on the left, and a main content panel on the right. So the set bar panel is where we usually put input controls like sliders, drop-down menus, or buttons. And right now, it just has a simple text placeholder, but in real app, this would be where users adjust the settings. And the main panel, like on the right side, is where we display the results, like plots, tables, or summaries. So this layout is useful for dashboards where users need to adjust the parameters on the side and see immediately how the output changes. So inside the main panel, we are using a tab set panel. So like here. So the tab panels allow multiple sections within the same app. So each tab can represent different types of content, making it useful for apps that require multiple views, such as summary reports, visualizations, and model outputs. So here we define like 3 different tabs. So we have tab 1, tab 2, and tab 3. So for each tab, we will have different tasks. Example test shows here. So instead of throwing everything on one page, tabs can switch between views smoothly without overwhelming the user. And there can be more than one panel within the layout, and panels can be nested with each other. Okay. So the next thing is a placeholder. So Shiny allows us to dynamically generate content by setting up placeholders for different types of outputs, such as plots, tables, and tests. So in the UI, we use functions like plot output, table output, or text output to reserve space for these elements. And these acts as empty containers that will later be filled with content. So on the server side, we will use functions like render plot, render table, and render test to actually generate and update the content dynamically. So these functions process the data and send the results to their corresponding placeholders in the UI. So this setup makes Shiny highly interactive because the outputs can be updated whenever the user changes an input. So it's easier to explore and analyze the data in real time. So the last component of our Shiny I'd like to introduce is the control widgets. So to make Shiny app fully interactive, we use control widgets that let users input values, select options, and manipulate data dynamically. So the Shiny provides a wide range of input controls, like the text box, numerical input slider, and some other things. So for example, a slider input can allow users to set a numeric range, like here. And a drop-down menu lets them choose between different categories, like here. I think this one is a drop-down menu. So by incorporating these widgets, the users can explore the data set, filter informations, and customize outputs in real time. So let's see a simple R Shiny demo. Okay, so since we don't have too much time, so we will like skip this part, but this part tells you how to arrange the Shiny app in multiple pages. Like you can, the Shiny demo 3, it combines the Shiny, the demo 1 and demo 2 into a single page. Like you don't have maybe 2 separate Shiny app, but you can show all the information in a single Shiny app. So if you're interested, you can check the Shiny app demo 3 to see how to combine the 2 separate Shiny app. So this is an open answer exercise tool. It just asks you to design your own plot with ggplotly to make it interactive. So if you have time and if you are interested, feel free to like create your own ggplot. So one useful resource I would like to share with you is friends don't let friends make bad graphs. So like creating effective visualizations is not just about making graphs look appealing. So it's about ensuring they communicate insights clearly and accurately. So this resource highlights common mistakes in data visualization and how to avoid them. For example, don't make violin plots for a small sample size, and you can see why it is important here. And don't make heat maps without checking outliers, and don't use the red or green and rainbow color scales. So you can check with this website, and it has all the informations here. So here are some useful resources for you to learn more about data visualization. And I highly recommend this website. And it's very useful because it not only provides the plot, and it also includes the code for generating this plot. So if you are interested, or if you want to generate a plot that we didn't mention in this workshop, you can refer to this website to see how to generate the plot and how to like and check the code they used to generate the plot. Yeah. And also here are some resources for how to create a R Shiny app. So R Shiny actually it's very convenient if you want to explain something or show your results to some maybe clinicians or some biostatisticians if they don't have any like experience in coding. So you can show the results to them and they can like click and select their inputs, the data scale they want to analyze. And then like the results will show automatically to them. So it's very user-friendly and convenient to convey the results. Yeah. And I think that's all for the data visualization sessions. Yeah, thank you.